Hi, my name is Bill. Welcome to Probability and Statistics for Everyone. This is video 4.3, where we're going to continue our journey of presenting, describing, and summarizing data. In this video, we're going to demonstrate how to present a box plot of a data set. So let's get started. This is a direct continuation of video 4.2, where we demonstrate how to find the quartiles of a data set. Q1, Q2, also called the median, and Q3. In fact, let's go ahead and pick up where we left off there. To the left are 10 random samples from a system or process, sorted from the smallest to the largest. And then to the right is a dot plot and EDF of those data points, with those three quartiles, the IQR, or interquartile range, and the range length displayed. Let's focus our attention on those two new values which showed up in the dot plot at the end of video 4.2, though I didn't draw your attention to them at the time. The range length, shown as RL on the plot, is the distance between the smallest value in the data and the largest value in the data. In the equation, notice we wrote y1 and yn. And recall that the y's are the so-called order statistics of that original data. So y1 and yn are the first and last value in the data list after the list has been sorted. The IQR is the distance between the smallest quartile and the largest quartile of the data, which some authors call the lower and upper quartiles. Both the range length and the IQR are measures of how spread out the data is. The IQR reports on the spread of the central 50% of the data, while the range length reports how spread out all of the data is. In a later video, after we finished assembling some of our tools for exploring data, like box plots, we'll discuss the relative merits of each approach, along with some others. Here we simply introduce them both because we'll need them for the box plots. Next, we need to introduce a concept called an outlier. An outlier is a data point that is different enough from most of the data to potentially not belong with the rest of the data. The determination of whether or not one or more data points are outliers is application dependent and sometimes subject to interpretation, as is what to do about them. We'll discuss outliers in much more detail in later videos, but I needed to briefly introduce the notion here because it's a concept that is embedded in the box plot. One method of identifying potential outliers is to use the IQR. A standard practice is to set a lower threshold, separating potential outliers from non-outliers, at 1.5 times the IQR below Q1, and an upper threshold at 1.5 times the IQR above Q3. This notation looks cumbersome, but it's shorthand for a lot of information. For example, the IQR_O is indicating that it's calculating an IQR-based outlier threshold. And then the LB or UB afterward is indicating whether it's a lower bound or upper bound. We can display those two IQR-based threshold detection bounds on the dot plot as vertical dotted lines. The dot plot is starting to get a little busy, but that's okay, because we now have everything we need to present a box plot of the data, or what some call a box and whisker plot of the data. Now we're going to fold it in on top of the dot plot, so we need to make some room for it. Once we have, we'll be ready to present that box plot. This box plot is oriented horizontally to match up with the dot plot. Sometimes box plots are oriented vertically, which we'll show an example of shortly. Let's break this box plot down. It begins with a central rectangle with vertical lines at the three quartiles. Then on either side of the rectangle, or box, are horizontal lines which some authors call whiskers. Now there's a lack of uniformity on how far out to extend those horizontal lines. Some authors only extend it to the two IQR-based bounds, while others extend it out all the way to the smallest and largest values. I'm not one for throwing data away at this point, so we'll extend all the way out to span all points. But we'll transition from a solid line to a dashed line once we're outside the IQR-based bounds. There are other variations of box plots that some authors prescribe, which we won't discuss in this video, because I think that in general they ask too much of a box plot. I think its real value is as a quick visual presentation of the data. The next thing for us to do is clean up the EDF and the dot plot, removing our temporary dashed and dotted lines, and what is left is my recommendation for a graphical first summary of any data set we receive. To demonstrate what this kind of graphical summary can offer, let's show what a similar display for another data set would look like. This time, it's another 100 samples from the same system or process that these first 10 samples came from. In order to compare them directly, we'll lay them side by side. As you consider these two displays, remember, these are 110 samples from just one system or process. First 10 samples on the left and another 100 on the right. I don't want to dig too deeply into interpreting these because that's outside the scope of this video, but there are a couple of things to observe. First, as we noted when we first introduced EDF plots, the display on the right appears less jagged because there are a larger number of smaller jumps in the plot. Second, still looking at the display on the right side, the concentration of points between 4-ish and 6.5-ish in the dot plot makes them blob up, and it's difficult to discern any pattern there other than a blob. Although the relatively steep slope on the EDF does tell us something about how much of the data is between those two values. Specifically, since this slope is between cumulative probabilities 0.2 and 0.9, more or less, it reveals that around 70% of the data is between these two values. Third, it's apparent in the display on the right that there is an interior structure to the randomness in the system or process that produced this data. One part of the structure is below that steep slope, then there is the steep slope region itself, and another part of the structure above that steep slope. Now that we know that it's there, we can kind of see it in the display on the left, but one takeaway from comparing the two side by side is that 10 samples aren't enough to be able to discern that kind of structure. For example, and this is a fourth observation, in the display on the left, that lone point at 9.439 looks like a potential outlier, a data point that doesn't belong with the rest. But we see in the display on the right that while it doesn't belong to the middle steep region, it does belong to the overall data set. And that's as deeply as I want to explore these two displays. The final thing I want to do is extract these two box plots and present them together into a single display. These are the vertically oriented box plots that I promised earlier, and a common graphical way of initially investigating multiple sample sets quickly. What we see are two boxes, which indicate pretty similar central or 50% ranges, and apparently very similar medians, as we would hope and expect from two sample sets collected from the same system or process. In videos 4.1, 4.2, and here in 4.3, we've explored ways to graphically summarize and present collected data, and potentially reduce it down to a set of descriptive statistics. That is the minimum value, the maximum value, and 3 quartiles, none of which need to be selected carefully to match the data. This is all part of a larger topic called nonparametric statistics, which we'll explain more fully in later videos. Next, however, in video 4.4, we'll explore histograms, which in general do need to be parameterized carefully to match the data, to avoid inconclusive or misleading outputs from being presented. So look out for that, and check back soon.